Hi, welcome to Analysis of Algorithms. We're going to do the homework problems for Chapter 6 today. Section 6.1, problems 1, 2, and 6, 6.2, problems 1 and 3, 6.3, problem 1, 6.4, 1 and 3. It's about heap sort, so some of the more technical things we're just going to go quickly over. Not technical, just some of the less boring things. Okay, so some of the less interesting things. What is the minimum and maximum? Okay, so 6.1-1. What is the minimum and maximum numbers of elements in a heap of height h? Okay, so let's do this. Okay, height h. So let's just do. Remember what a heap is. Okay, so this has height 0, 1, 2, 3. Okay, now the minimum number is 1. Okay, so we're going to write it as 2 to the 0 plus 2 to the 1 plus 2 to the 2. There's 4 here, 1, 2, 3, 4. Okay, and the minimum number is going to be, let's say, with one more. Okay, so this is height 0, 1, 2. Let's say we're dealing with height, let's say we're dealing with height 3, so this would be, this whole tree would be of height 3, and the minimum number would be 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this would be 2 to the third. Okay, I'd like to write it another way. So we have the geometric series. Let's remember what the geometric series says. It says I equals 0 to h, okay, of 2 to the I is 2 to the I plus 1 minus 1. I'm sorry, 2 to the h plus 1 minus 1. So let's do this. H is equal to 3. So that would be 2 to the 4 minus 1. That's the max. That's how, if all of them were filled. So that would be all of them filled. So let's just do it. That would be 2 to the 4 is 2, 4, 8, 16 minus 1. That would be 15. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so that would be the maximum. Okay, the minimum is very simple. H is equal to 2. Okay, so then you plug it into that formula, you get 2 to the 3 minus 1, but then you need one more to bring it to the next level, so plus 1, which is 2 to the 3 is 8, minus 1 plus 1 is 8. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's do it in general. Okay, the minimum is, let's do the max. The maximum is everything's full till there, so that's 2 to the h plus 1 minus 1. Okay, 2 to the h, that's the height. So you go to the next one, that's just the geometric formula. Okay, the minimum is basically 2 to the h minus 1, and then you got to do the geometric formula, so that's plus 1, okay, minus 1, that's how many there are in the till that level, and then add one more to get the next level. So that's going to be the minimum. Okay, now this could obviously be shrunk. H minus 1 plus 1, this is equal to 2 to the h. Okay, minus 1 plus 1 cancels out, and you have that. Okay? Okay, so again, the whole thing is, that's a tree of one less layer, that's one more, so that brings to the right level, and if you wanted all of them, you'd have just a tree, a complete tree of that level. Okay, so that's not hard. So this is the final answer. Okay, 6.1, number 2. Let's read the question. Show that an n-element heap has height log of n, n element heap has height log n. Okay, actually we did this in class, okay, and basically we can look at it the other way. Okay, and basically we look at it the other way. So, but let's do some regular things. Let's do a real live example. Okay, so how many elements does this have? One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, log of 12. That's tough. Well, that's 3 and something. Let's see. Log of 9, no, of 8 equals 3. Log of 16 is equal to 4. So this is 3 and something. So the floor of that is 3. Okay? 1, 2, I'm sorry, 0, 1, 2, 3. So that's correct. Okay. The idea is as follows. That's the maximum number. That's the maximum. If you have the height, we just did. The height is 2 to the. If you have the height h, the number of elements in your thing is 2 to the h plus 1 minus 1. Okay. Now, no, it's more than n. Okay. Okay. Anyways, the answer is you solve for h. And you get something like h is more than n plus 1 log of n plus 1. Something like that. Okay. Anyways, let's be more exact. Okay. Okay, so the way to do this is as follows. The minimum heap is 2 to the h. The max is 2 to the h plus 1 minus 1. Okay, so something like that. Okay, this is 2 to the h plus 1. Just forget about the minus 1. Okay? Okay, great. So this is the smallest amount of nodes it can have. Now just solve for h. So you solve for h by taking logs on both sides. So you get h is less than or equal to log of n, which is less than or equal to h plus 1. Okay? And so you have, it's somewhere, it's an integer between h and h plus 1. Okay? So you have to do this. H is less than log of n floor. Okay, maybe I'm wrong about this. Okay, got to think about it. Okay, that's section 6.1, number 2. Let's do number 6. Okay, number 6 is very easy. They give you an array and they ask you if it's a max heap. Let's just write down the array. 23, 17, 14, 6, 13, 10, 1, 5, 7, and 12. Here's the numbers to the heap. Okay, this is the numbers of the array. They want you to put it down as a heap, so let's do it. 23 has 2 children. We're reading from left to right and putting them in. 17, 14, 6, 13, 10, 1, 5, 7, 12. Okay, he's larger than his children, he's larger than his children, he's larger than his children. He is not larger than his children. Okay, so the answer is no. Look at that, fancy. Okay, so that takes care of that. That was pretty simple. Okay, next. Section 6.2. Section 6.2. Number 1. Okay. Illustrate the operation of max heapify 1 a comma 3 on this array. So let's just write down the things. So I'm doing section 6.2, number 1, 27, 17, 3, 16, 13, 10, 1, 5, 7, 12, 4, 8, 9, 0. Okay, so what they first want us to do is put it into some type of heap. Well, it's not really going to be a heap, but put it into a almost complete binary tree, and then fix it from point 3. So let's do it. So 27 has 2 children, 17 and 3. Okay, 17 has 2 children, 16 and 13. 3 has 2 children, 10 and 1. 16 has 5 and 7. 13 has 12 and 4. 10 has 8 and 9. And this has 0. Let's just make sure that I'm right. Okay. 27, 17, 13, 12 and 4, 8 and 9, 0. Perfect. Okay. And now what they want is they want us to fix it from point number 3. Okay, the third point. 0, 1, I'm sorry, 1, 2, 3. Okay, I think that's correct. Let's just make sure. Okay, so let's do it. I'm going to do it in a different color. So this is I. Okay, and we want to heapify. How do you heapify? You find the maximum of these 3 elements. The maximum is 10. So basically, these 2 are going to swap. Okay, and we have an eraser, so we can do that. Okay. Oh, so the maximum is going to swap, and so we're going to go there. So this is going to become 10, and this is going to become 3. Okay, and then we recursively call it. Okay, what's the maximum of these 3? 3, 8, and 9, and the answer is 9. And so this is going to swap. Okay, so this becomes 9, and this becomes 3. And we're finished. Okay, it trickles down. The 3 was up here, it trickled down till here. This is as I is equal to 3. Okay, so that takes care of that. That section, let's just read the question again. Use figure 6.2 as a model, illustrate the operation of max heap. Okay, on the array like that. Okay, number 3. What is the effect of calling max heapify when the element a of I is larger than its children? Okay, so we're doing section 6.2, 1, 3. So basically you have the father and you have two children, we call them left and right, okay, and if he's the largest, then it doesn't, so that you don't switch, and it doesn't call its children. It doesn't go recursively. So as soon as, if the father is larger than the left son and the right son, then it stops right there and doesn't do anything. That answers number 3. Okay, next, section 6.3, number 1. Section 6.3, number 1. Okay, they want you to use this figure 6.3. They're going to give you an array, and they want you to max heapify. So, I'm sorry, they want you to build max heap. So let's do it. Okay, so let's write the numbers. So I'm doing section 6.3, number 1. Okay, 5, 3, 17, 10, 84, 19, 6, 22, 9. Let's just make sure we have that right. 5, 3, 17, 10, 84, 19, 6, 22, and 9. So first thing we do is build a heap out of it. Okay, so let's do it. I'm sorry, build an almost complete binary tree. 5, 3, 17, 10, 84, 19, 6, 22, 9. Okay, that takes care of that. Okay, now, first thing to notice is this, just the 9 by itself, is a heap. This is a heap. This is a heap. This is a heap. This is a heap. And so we start from here. Okay, we're going to go backwards, here, 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 and here. Okay, and heapify at each point. Okay, so we'll do a few and then we'll rewrite it. But basically, okay, let's do this. Okay, the maximum of these 3 is 22, so we're going to swap that. So this becomes 22 and this becomes 10. Okay, that takes care of that. Now we're going to go here. The maximum of these 3, we're up to here. We're heapifying from here. The maximum of these 3 is 19. So this becomes 19. This becomes 17. Okay, let's just rewrite 5, 3, 19. This is 22, 84. This is 17, 6, 10, 9. Okay, and now we're up to here. Okay, so let's max heapify. So we max heapify, I'm sorry, we heapify this, okay, and we swap this. This becomes 84, this becomes 3, and we don't have to go further because he has no children. Okay, and finally we go up here and we max heapify. So let's do it. We heapify. So this becomes 84. He is the highest. He becomes, ooh, hold on, go here. Yeah, okay. 5 goes here. Okay, so we swap these 2. Okay, and now we have to trickle down. From these 3, 5, 22, and 3, what's the max? Answer 22. So 22 goes up here, 5 goes here. Now we heapify from this point of view. 10 goes up, and 5 goes down. Okay. Let me just make sure I got it right. So, I got it right. This is 84, 22, 19, 10, 3, 17, 6, 5, and 9. Perfect. Okay, so that's section 6.3, number 1. Okay, good. Now, section 6.4, number 1. Let's read it. This is the actual heap sort algorithm using figure 6.4. That's this 6.4 with the dots at the end. Illustrate the operation of heap sort on the array. Let's do it. 5, 13, 2, 25, 7, 17, 28, and 4. 28 and 4. Okay? Okay, so first thing first is we have to make a heap out of it. So let's make a heap out of it. 5, 13, 2, 25, 7, 17, 20, 8, and 4. Okay, so that takes care of that. That's not a heap, but we can that's a almost complete binary tree, but that's a heap, that's a heap, that's a heap, that's a heap, that's a heap. That happens to be a heap already. That is not a heap, so let's make it into a heap. What's larger? 2, 17, and 20. The answer is 20, so let's bring 20 up here, 2 down there. Okay, let's heapify from here. What's larger? 13, 25, or 7. Answer 25 goes up, 13 goes down. That's a heap, so leave it alone. Okay, and finally, all the way up top, what's larger? 5, 25, or 20. Answer 25, so this becomes 25, this becomes 5, okay, and now we have to trickle down. 5, 13, or 7, what's larger? 13, so 13 goes here, 5 goes here. What's larger? 5, 8, or 4, answer 8, so this becomes 8, and this becomes 5. Okay, okay, good. So now let's just rewrite it. 25, 13, 20, 8, 7, 17, 2, 5, and 4. Let me just check my answer. Hold on, don't move, don't move. Okay. Five, 13, 20, 8, 7, 17, 2, 5, and 4. Okay, that works. So that is our heap. Now, what we're going to do is, we're going to slowly, what do? We pop off the top and pull it to the end. Okay? And then we put that on top. So let's do this with colored chalk. So the 25, so the 25 goes here, not connected to anything. Okay, and the 4 goes here, and now we trickle down. So we trickle down, this becomes 20, this becomes 4, now we switch here, 4 and 17. Okay, good. Okay, now 25 is the last element of the array, 20 is the top, so we swap that. So let's erase the connection, okay, and put the 20 here, and the 4 goes down. I'm sorry, 20 there, and the 4 goes down. No. And the 4 goes up. No. And the 5 goes up. Okay. No, wait. We put the 20 on top, the 20 goes up, and the 5 goes up. Okay, hold on, don't move. Okay. Anyways, then 5, 13, and 17, so the 5 goes here, and the 17 goes here. 5, 4, and 2, that's finished. So now we have, let's rewrite. So we have 17, 13, and 5, 8, and 7, 4, and 2, and besides that we have 20, that's not on our list, and 25. Okay? Okay, good. So now I'm going to pull off the top element. I'm going to replace it with the bottom element. So 2 goes here, and 17 goes here. Now we heapify. 13 goes up, 2 goes down. Heapify, 8 goes up, 2 goes down, and we're good. Okay, great. Now, pull off the max of the heap, so, and put the bottom there, so this 13 is there. So notice we're increasing, 13, 17, 20, 23. Okay? And you keep on doing this. So I have to heapify here, so 8 goes up, 4 goes down, 7 goes up, 4 goes down, and we keep on doing this. Okay, I'm finished with this. I don't want to do any more. It's not hard. It's just a lot of bookkeeping, but one more. So 8 will go here, 8, 13, 17, 20, 23, and 4 goes up. And then you heapify. Okay, so that takes care of 6.4, number 1. Okay? Now, the last question is an analysis of algorithms class. Question. This is a real thing. What is the running time of heap sort on an array A of length n that is already sorted in increasing order? What about decreasing order? Okay, so here's the thing. Increasing order so first of all, you have to make, so let's just do a funny increasing. 1, 2, 3, 4, 5, 6, 10, let's say. Okay, so when you have to make this a heap first. So that's 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now again, this is a heap, this is a heap, this is a heap, this is a heap, this is not, and it'll have to trickle down. Okay? So just to make this a heap, you need the following. Just to make it a heap, you need the following. You need a half n, because that's how many numbers you have, that you have to heapify, and each one of them, okay, is going to be n log n. It's going to have to trickle down. All the things are going to have to trickle down. And that's the key point. That's the main difference between increasing order and decreasing order. Okay? It's going to have to trickle down. Okay, so that's just to make the heap. Once you make the heap, let's go through what you have to do. You have to pull off the top. You're going to have to do this n times. Okay? Pull off the top, put it on the bottom, take the bottom and put it on top, and then you have to bring that bottom all the way down. So it's going to be heapify on each one of those. I'm sorry, this is just log n, okay, because this is just log n, at most log n. So, so the main point is that when it's increasing, you have to do this by half of them, and then for each one, pull it off, and then log n for heapify at each point. Okay. Now the main difference is by decreasing order. Okay. Then it's much easier to make the heap. Let's do an example. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay? Well, 10 has two children, 9 and 8. 9 has two children, 7 and 6. 8 has 5 and 4. Okay? 3 and 2, 1. Okay, the main point is that's already a heap. Okay, that's already a heap. Okay, that has every father, because it's decreasing, every father is larger than every child, than all its children. Okay, and so we don't have to do it. So it won't travel down. So let's go through this. We don't look at this because that's a heap, that's a heap, that's a heap, that's a heap, that's a heap. That we just do one check and it's a heap. One check and it's a heap. We don't trickle down. Okay, so basically it's half n, because that's what we have to do checking. We have to compare the fathers to the children by half of them. Okay, if you want to be careful, so you have to do 2n, because you have to do two comparisons, the left and the right and the father. You have to compare three things, the father, the left, and the right. So that's that. But you have to do it for half n. But that's it. It's not going to trickle down because you don't need heapify. Plus n, once you do have a heap, you pull off the top, you put it in the bottom, you swap the top and the bottom. That's regular n log n. Okay? So for a decreasing array, it's a half n plus n log n. Okay? Which of course is O of n log n. Okay? So that's chapter 6. Thank you.